I hope it's obvious to you now that to enable this heterogeneous integration in your smartphone or your tablet device, to reduce this interconnect length, also to reduce your form factor, the only way to do that is to stack these chips either on top or side by side. So there are two ways you could do it. You could either stack it in a 3D manner, which is a more revolutionary approach, where you take your, say you had a memory chip and you had a logic chip, so you stack your memory on top of your logic and you connect them using this through silicon via, which enable this connection between your memory and your logic. A more evolutionary approach, which is currently in production now, is using this thing called 2.5D, or placing these chips on side by side of each other, and then you use the silicon interposers, which is a passive layer. Essentially what it means is that it doesn't do any processing, or it doesn't add any functionality. Its only purpose is to route these signal lines between your memory and your logic. So we use this silicon interposer to route the signal between our memory and our logic chip. We also use the silicon interposer, which has through silicon vias. So this silicon interposer has through silicon vias, which help this overall package to connect it to the PCB to bring the power supply in, and to connect this overall package to your PCB. So the more revolutionary approach that I talked about was essentially going 3D. So what it requires is, it requires this through silicon via through these chips, which are all active. So all of these are active layers, this memory and DRAM and your microprocessor, all of these are active layers. And whenever you are enabling this through silicon vias through your active chip, a lot of concerns come into picture. So one of the concern is obviously each of these chips will heat up. So one of the major concern is thermal management. Another concern is with stress. So this through silicon via, the process of making this through silicon via produces a lot of inherent stress in the chips, and so you have to keep a keep out zone around each of these through silicon via to manage the stress in your chip. So people looked at it and said, gee, this looks way too hard, so let's give it to the lab guys to play around with it for a few years. And what they end up producing in the meantime was this thing called 2.5D. So the way this works is you have a silicon interposer. So you have this silicon layer, which is used to route all your signals between your microprocessor and your DRAM, and between your DRAM and your NAND flash. And you could then have these through silicon vias over here, and then this would be used to connect this overall chip to the package below, to bring in the power supply voltage and route all the signals to your PCB. And so you get around, since the silicon interposer is a passive layer, so you don't have to worry about thermal issues here. You don't have to worry about stress, because even if this thing heats up, this silicon interposer heats up, or it has a lot of stress, it doesn't affect your performance much, because the silicon is essentially a passive layer. It's not doing any signal processing on its own. So all it's doing is it's routing the connections between your different chips. So this is something which was actually introduced by a company called Xilinx in 2011. So there are two big announcements in the semiconductor industry in 2011. One obviously was the FinFET technology introduced by Intel. The second big announcement was this 2.5D technology, or interposer, introduced by Xilinx. And so Xilinx is a company which makes these FPGA chips, or field programmable gate arrays. And what they did in this chip was they took 4 of these FPGA chips, which were made using a 28 nanometer technology, and they connected them on this single die using a silicon interposer. So a zoomed in view of this is shown over here. So what they did was they took each of these FPGA chips made at a 28 nanometer node technology, and then they use these micro bumps to connect it to this use this micro bumps to connect it to this silicon interposer. And the silicon interposer was made during a different technology. So since you don't need that fine routing here, they use a 65 nanometer technology to make this silicon interposer, and it has 4 levels of these wiring to connect these FPGA chips. And then you place them side by side. Also, to bring in the power supply and to connect it to your PCB, you have these through silicon via. So you have these through silicon via inside your silicon interposer to bring in your power supply and connect your overall package to your PCB. So this is showing another image. So you can see that you can see this interposer layer here, and you can see one of these chips here, and these are connected to the interposer using this micro bumps. And you can also spot this TSV through silicon via, which are essentially connecting this overall die to your PCB. And another thing this technology allowed Xilinx to do was actually achieve a reduction in their overall cost. So why was this? You know, they introduced a new technology, they did all this fancy interposer thing. So why was this cost reduction possible? So the reason for that is, as you increase your chip size, so you have a chip size of say X, and you want to enable a memory chip which is 4 times. So if you make your chip which is 4 times the size of this, your yield actually substantially goes down. Instead, if you made 4 of these chips and you could connect them using this interposer, you could achieve a much higher yield. So that's what is shown here. They were actually able to achieve a linear increase in the cost with increase in your memory size, or with increase in your area of your overall memory capacity, as compared to if you make it in one single chip, you would actually you'll achieve an exponential increase in cost. So it helps in reducing your cost as well. So a question I want to ask you is, why make this interposer? Why make this interposer in silicon? Why not just use a PCB for making this? So there are 2 options we can have for making this interposer material. You could either make it in silicon, or you could make it actually in the PCB material itself. So one of the reasons that you make it in this silicon is that now you can use this VLSI technology. For example, in this case, you used 65 nanometer VLSI technology, and using this you could enable a much higher IO density, or you could place these interconnections very close to each other, because now you're using the VLSI technology available in silicon. Another reason of doing it in silicon is from the point of view of coefficient of thermal expansion, or CTE. So silicon has a CTE of 2.5 parts per million. What it means that for every Kelvin increase in your temperature in X direction, the silicon chip would expand 2.5 parts per million. A PCB, the best of the PCB material that you can get, has a coefficient of thermal expansion which is at least 5 times greater than that of silicon. So the minimum you can achieve in a PCB material is 15 parts per million. So if you had a silicon chip placed on a PCB with very tight interconnections, and the silicon chip would be heating up your PCB, there will be a large amount of stress built up into this PCB, which is fine if these interconnections are far apart, but it can cause a havoc if these interconnects are very tightly spaced. So that's another reason why we use silicon is the material of choice for making this interposer.